In this video, we'll talk about the process of row reduction and how we can use it to simplify augmented matrices to let us solve systems of equations. So row reduction is this process we're going to use to abstract away solving systems of equations to just working with these matrices and being able to simplify these matrices down to the nice forms that we've seen previously that will help us get to these solutions. To do row reduction, we have the following three elementary row operations that we're allowed to perform on matrices. And we're going to perform them in specific orders and ways to get to simplified forms of this augmented matrix. So the operations are the following. One, I can swap two rows of a matrix. Operation two, I can multiply the row of a matrix by any real number. In option three, I can add some multiple of one row to another row. And it shouldn't be too surprising that this is the operations we're allowed to perform, as these were the exact same three things we could do with systems of equations. We could swap two equations, multiply by a number, or add one to another. Right? These are the same three operations we could do on equations. We're just going to now do them on matrices instead. So we've abstracted away the variables part and are just solving the matrix as itself. This process here you may also refer to as Gaussian elimination, or Gauss-Jordan elimination as well. But the idea is the same. The idea is I'm trying to do elimination on this matrix to get me to a simpler form that I can analyze. Now, for solving systems of equations, we want to apply this process to the augmented matrix that comes from the system. This process can be applied to any matrix for any reason, and there's reasons you might want to do this. But in this particular instance, we want to take the augmented matrix from the system and apply this process to reduce the matrix. Now, what are we aiming towards? Well, we're aiming towards a simplified form where we can read off the answer. That's referred to as the row echelon form of the matrix. So we want to use this row reduction process to get down to either the row echelon form or the reduced row echelon form, depending on what kind of problem you're trying to solve. So to characterize the row echelon form, it has the following properties. The leading entry, or the first non-zero entry in each row, is a 1. The leading entry of each row is always strictly to the right of any that are above it. And then finally, any entries below a leading entry are all 0. You will sometimes hear these sort of first non-zero entries or leading entries referred to as pivots in this case. But what it's basically saying is that these first non-zero entries, pivots, have to start from the left, always move to the right as you move down, and they have to all be 1s. So an example of that would be something like this matrix here. This matrix here is in row echelon form. Let's look at the first non-zero entry in each row, first coming from the left. So these are all 1, which they have to be by the first property there. They have to be strictly to the right of any above them. So right, this is in the first column, second column, fourth column, that's fine, that's good. And anything below a leading 1 is all 0. These two are 0 here, this is a 0 here. So this is in row echelon form. And if you think about it, this gives me a really easy way to read off solutions to a system of equations if I have a system here. Right, this last one tells me that x4 is 2. Done. I then have that, can plug that in here to tell me that x2 plus x4 is 3, or x2 must be 1, because I already know that x4 is 2. And I can plug those back in up here as well. So this gives you a form for which you can read off at least one answer, and then use back substitution to find the entire solution from there. Now there is a further step you could take in this process, and that is getting to the reduced row echelon form. And that is the same as the row echelon form, plus all the entries above these leading 1 pivots are also 0. The point is basically this process does the back substitution for you. So the matrix we had before is in row echelon form, but not reduced row echelon form, because while this 0 is good, there are entries above this leading 1 that are not 0. So we could make it into reduced row echelon form by doing some operations, and that would give us something like this. And now this is in reduced row echelon form because now everything above the leading 1s is also 0. And the point is this makes it even easier to read off the solution. x4 is 2. x2 is 1, and then I have a free variable here in my first equation. So that is what we can do with the process, and that's our goal. We'll next want to see what we can actually do and how we actually work out this process to get to these reduced form matrices.